Energy in Earth's atmosphere. In this lesson we'll talk about how energy from the sun travels to our Earth, and we'll also talk about what happens to the sun's energy when it reaches our planet. The electromagnetic spectrum, or electromagnetic waves, is the way in which energy from our sun travels across the vacuum of space and it reaches Earth. Most of this energy is visible light, so it's the light that you and I see. Some of it is infrared radiation, so heat radiation. Some of it is also ultraviolet radiation, and we'll talk about what the difference is between each of these. Visible light. Visible light is all of the colors that we see. Roy G. Biv: red, orange, yellow, green, blue, indigo, and violet. All of these are the colors that we interpret with our eyes. The reason that we have different colors is due to the fact that each color has its own specific wavelength. Red and orange have long wavelengths. Blue and violet have short wavelengths. The nonvisible radiation. Nonvisible radiation, as it suggests, is the radiation or the energy that the sun produces that we cannot see. The direct transfer of energy by electromagnetic waves is called radiation. There are two types of non-visible radiation. Infrared radiation, and these are the wavelengths that are longer than red light. Infrared radiation we typically interpret in the form of heat. So we cannot see infrared radiation, however we can feel it when it comes in contact with our skin. There are certain organisms that can detect infrared radiation. For example, rattlesnakes. They can sense heat using their tongue. Ultraviolet radiation is the form of electromagnetic energy that has wavelengths that are shorter than violet light. We become familiar with UV light when we receive a sunburn. Those short wavelengths burn our skin. So looking at this picture inside of your notes, we know that radiation from the sun travels to Earth in the form of the electromagnetic spectrum, or electromagnetic waves. The center portion are the visible light spectrum. We need to know what are the two on each side. Notice that the ones on the left have a larger wavelength and the ones on the right have a shorter wavelength. So infrared radiation is going to be the heat radiation that is on the left side of the red visible light, so it's the longer wavelengths than red light. The center is going to be visible light, so the light spectrum that we can actually see. And then the shorter wavelengths than violet are ultraviolet radiation, and these are the radiations that cause sunburn. Energy in Earth's atmosphere. Some of these different forms of the electromagnetic spectrum are easily transferred through the atmosphere. Others are not. You will notice that a lot of the infrared radiation that hits our atmosphere is absorbed by the stratosphere and the mesosphere. Also, ultraviolet radiation is absorbed in the mesosphere. Part of the thermosphere absorbs it as well. And then there's almost little to none that makes it all the way through the stratosphere. Also notice that visible light makes it through all the layers of the atmosphere. The upper atmosphere. The thermosphere and the mesosphere both absorb the majority of the ultraviolet and infrared radiation. In the troposphere, the clouds act as mirrors, and they help to reflect sunlight back into space. Some things on Earth's surface reflect light as well. We call this Earth's albedo. When we have things like snow on the ground, it increases Earth's albedo. So the reflectivity of our planet increases when we have a large amount of snow cover. The process of reflecting light is called scattering. Clouds scatter light. Dust particles in the atmosphere help to scatter light. Gases in the atmosphere also scatter light. Looking at the graph and looking at the different materials down at the very bottom, we are going to create a graph that shows a bar for the percent reflected of each of the following materials: asphalt, fresh snow, a deciduous forest, and dry soil. So the title of our graph is going to be the amount of energy reflected. We need to put a scale for the amount reflected on the left side of our graph. So 0 being 0% reflected, 20% reflected, 40% reflected, 60% reflected, 80, and 100% reflected. So asphalt has a reflectivity of 5 to 10%. So I'm going to draw my graph up somewhere in that general area. Fresh snow has a reflectivity of 80 to 90%. So I'm going to graph, and in this case I graphed it all the way up to 90%. A deciduous forest has a reflectivity of 15 to 20%. And I went with the higher amount on this one, so I put it up to 20%. And then finally, 20 to 25% reflected for dry soil. Somewhere close to that. That would be about 25% reflected. Please make sure that this graph is completed within your note sheet. Looking at this picture that is also in your note sheet, and looking at the amount of energy that is absorbed or reflected by our planet with regard to solar energy. We're going to complete each sentence with a word from the bank above. And the bank includes reflected, absorbed, and radiated. So looking at the top here, about 25% of incoming sunlight is reflected by clouds, dust, and gas in the atmosphere. About 50% is absorbed by Earth's surface, and this helps to heat the land and the water. About 20% is absorbed by gases and particles in the atmosphere, which is good. This process helps us to heat our planet. Some absorbed energy is radiated back into the atmosphere. As energy is radiated back into the atmosphere, it allows the temperature on our planet to slowly increase. And then about 5% is reflected back by the surface and the atmosphere. Earth's energy budget. When we're talking about Earth's energy budget, we're going to be talking about the total amount of incoming solar radiation that we get on a daily basis. Earth's energy budget is 100% on any given day. Local areas may end up with more or less energy depending upon cloud cover or moisture in the atmosphere, but the Earth as a whole has 100% of the same amount of incoming solar radiation on a daily basis. So our surface radiates some energy back into the atmosphere, and as it radiates it, it's in the form of infrared radiation, heat energy. Some of the energy is absorbed by materials in the atmosphere, so dust and other debris, maybe even water vapor. The materials that absorb energy include water vapor, carbon dioxide, methane, and a number of other gases. As our atmosphere traps heat and retains heat, our temperatures increase. The holding of heat in our atmosphere is called the greenhouse effect. It's important for maintaining the temperature that we have in our atmosphere. Often when we hear about the greenhouse effect, we hear a negative connotation. The greenhouse effect is not bad. In fact, the greenhouse effect is good for us. Without the greenhouse effect, our temperatures would become extremely cold at nighttime hours. And it would also increase the temperature during the day well above the extremes that we get currently. So the greenhouse effect helps to regulate our temperature on our planet. It keeps us from getting too hot during the daylight hours, and it keeps us from getting too cold at the nighttime hours. If we have too much heat retention, however, we can have problems with climates on our planet, which is what many scientists are starting to fear. They're starting to fear that our atmosphere is retaining too much heat, thereby increasing atmospheric temperatures in climates where those temperatures aren't supposed to be that warm. So the greenhouse effect is a natural heat trapping process. What do you think the sequence of events is that occurs with regard to this picture? Well, we know that number one has to be the sun's energy reaches Earth. So as that energy comes in, it reaches our Earth, and it is turned into long-wave radiation, into infrared radiation, which is heat. There, Earth's surface is heated. Some heat is radiated off into space, and some is radiated back into the gases of the atmosphere, and the gases in the atmosphere trap that heat, allowing our temperatures to increase.